In this chapter, we will cover the workflow and definition for creating slots in the triangulated mesh faces. Let's go over the workflow before starting with the script. Slot profiles are governed by the type of joinery. In some cases where rivets hold the strips together, you may create circular openings at designed locations. For this exercise, we will provide rectangular slots of size 0.8 by 1.5 mm. One slot will be provided for each triangular face at the diagonal intersection, such that a cable tie can loop through and lock in place. Slots will be created by first creating the rectangular slot profile on the triangular faces of warp strips, then extruding the rectangular profile to intersect the adjoining triangular face of the weft strips, and finally using intersect function to get the face with rectangular slots. Let's start building the definition. Take the triangular faces of the warp list and deconstruct the mesh. Extract vertices at index 0 and 2, from each branch of vertices. Make a line between the two vertices, and we get the diagonal edge. For the rectangular profile, we need to identify the plane of the triangular face and starting point for the rectangle. The plane can be created using the construct plane component. It requires an origin point, x vector, and a y vector. X vector can be formed by creating a vector 2 point between the start and end points of the diagonal. Bring the vector 2 point component into the canvas. Use the endpoints and connect it to points A and B. For the second vector, use the face normal function to extract the center point on the face. And project it on the diagonal line using the curve closest point component. Create a vector between the center point and the output from curve closest point, and that's the second vector for constructing the plane. For the origin point, we will take the midpoint of the diagonal line, and move it by 1.5 mm towards the direction of the second vector. Set the second vector to an amplitude of 1.5 using the amplitude function. Use the move command to translate the midpoint with this new vector. And we have the origin point to construct the plane. Connect all three inputs, the origin, first vector, and second vector, into the construct plane component. If the planes appear too big on your Rhino viewport, you will have to change their preview size by going to the Display tab in the menu bar, clicking on the Preview Plane Size option, and setting the size to 5. If everything is done correctly as per the video, you should have one plane for each triangular face. Now we can construct the rectangular profile using this plane and rectangle component. Bring the rectangle component into the canvas. Connect the plane into plane input. X dimension is 1.5 millimeters. And Y dimension is 0.8 units. The resulting rectangles are co-planar with their respective triangular mesh, but skewed in alignment. This is because the rectangle component creates a rectangle from the corner. To fix this, use the x-vector from the construct plane, change its amplitude to -0.75 mm, that is half of the x-dimension of the rectangle. Rather than assigning the value manually, we will multiply 1.5 with -0.5, and then set the amplitude of x-vector. The negative value of the vector will reverse the direction. Use this vector to translate the rectangle position. And it should be aligned now. With the rectangles in place, we need to extrude it now. For extrusion, we need the Z vector of the constructed plane. Use deconstruct plane component to extract the Z vector of all the planes. Set the amplitude of Z vector to 5. Use this vector to extrude the rectangular profile. Based on the direction of the vector, the extrusion may or may not intersect with the adjoining weft strips. To ensure they intersect, multiply the extrusion vector with -0.5. And use it with the move component to translate the extruded geometry. We use these warp faces to intersect with the extruded rectangle. Bring B-reps intersection function into the canvas. Extract the face boundaries on each triangular mesh face, and create a surface from it. Graft, simplify, and connect the triangular surfaces into B-reps A, and the extruded rectangular profiles into B-reps B. This gives us a list of curves resulting from these B-reps intersections, which are rectangular profiles. Isolate the triangular polyline boundary of the mesh faces using face boundaries. Graft, simplify, and merge the list of triangular polylines and rectangular profiles. Such that the polyline and rectangle belonging to a single triangle is grouped together in a single branch. Create a surface from this combined list, by connecting it to boundary surface component. And there we have it. The first list of triangular faces with rectangular slots representing the warp strips. For weft strips, extract the face boundaries on each triangular mesh face, and create a surface from it. We use these surfaces to intersect with the extruded rectangle. Bring B-reps intersection function into the canvas. Graft, simplify, and connect the triangular surfaces into B-reps A, and the extruded rectangular profiles into B-reps B. This gives us a list of curves resulting from these B-reps intersections, which are rectangular profiles. Graft, simplify, and merge the triangular face boundary of weft strips, and rectangular profiles, like we did for the warp faces. Use boundary surface to create the triangular faces with rectangular profiles. Now that we have the two lists of triangular faces with rectangular slot profiles, we must check the orientation of these triangular faces and ensure they all face in the same direction. If we evaluate the triangular face for its normal direction, we find that all triangular faces are not oriented in the same direction. This will lead to complications in unrolling the B-reps strip, which uses the orientation of individual surfaces to determine the orientation of the unrolled strip. To align these triangular faces, we take the warp list, isolate a point on each triangular surface and move it 0.5 mm along the normal vector, and negative 0.5 mm along the normal vector. Then check the proximity of this translated point from the triangle surface on the weft list. To check for similar orientation, the distance of 0.5 mm translated point should be greater than the negative 0.5 mm translated point. Isolate a point on the surface using Evaluate Surface. Multiply the normal vector with 0.5 and negative 0.5 and move the point. This gives 2 points for every triangular surface. Evaluate their distance from the list of triangular surfaces in the weft list. The resulting distance output is a data tree that has 2 numeric data in each branch. We must check if the first number is greater than the second number. Use list item to isolate index 0 and 1 of each branch. Use a mathematical operator to check if the first list is greater than the second. Use the resulting Boolean statement to dispatch the list of triangular faces. And flip the triangular surfaces from list B of the dispatch output. Merge list A, and flip list B into a single list. Collect the surfaces into a surface container component. Check if the surfaces are now aligned. Repeat the same steps for weft triangular surfaces as well. Copy this definition, and replace the warp list as the test surfaces for the surface closest point. This gives us two lists of warp and weft triangular faces with all faces aligned in orientation. Let's analyze their data structure. Each list has 2048 branches, and each list represents one layer of strips. If we read the path of these branches, they have two hierarchies. The first number relates to the index of the initial quad face, and the second number specifies the triangle number. Let's trim these lists, so the outer branch is collapsed, and the triangles can be joined into quads. Connect the list of triangular faces into trim tree. And connect the trimmed list into the breps join command. Merge both lists of joined breps into a single list, and flatten the output. This resulting data tree is similar to the data tree we had in the beginning when we merged the warp and weft quad faces into a single list. At this stage, we will retrieve the list of indices that we highlighted in the previous video, which will help us reorganize our new list of quads as per warp and weft strip quads. Use the sort list component. Flatten the keys input, and connect the indices to the keys. Connect the new list of quads to values A. The sorting function will sort the indices in ascending order and simultaneously reorganize the list of quad breps. The resulting list of quad breps has 2048 items. Index 0 to 1023 represents the quads on warp layer, and index 1024 to 2047 represents the quads in weft layer. Let's partition this list into two. Take the list length, divide it by 2. And use the number to partition the list on warp and weft layer quads. From these two lists, we must partition this list further into separate branches as per the strips. To do that, we must trace back to the starting of the triangulation step, where we had the initial list of quad surfaces. Use the list length command to extract the length of each branch. Flatten the output from list length. Collect the list length into a number container and bring it forwards towards the right of the definition. Use it as partition size. So we have two lists of numbers. One for warp list, and the other for weft list. Segregate warp and weft layers using explode tree component. The first output is warp layer, and the second output is weft layer. Partition these lists of quads with their respective partition numbers. Join the resulting B-reps list. And we get the 48 branches each for warp and weft list, with one joined B-reps strip in each branch. These two lists contain the final strips that will be unrolled, tagged, nested for fabrication. In the next chapter, we will cover unrolling and tagging of these strips for fabrication.